So here's something worth thinking about as you settle in tonight. Right now, somewhere on this planet, there are about 440 nuclear reactors humming away, and each one of them is doing something that would have sounded like pure fantasy just 150 years ago. They're splitting atoms. Atoms. These unimaginably tiny things that you and I and everything around us are made of. And they're using the energy released from that splitting to boil water, spin turbines, and push electricity into the grid so that someone, somewhere, can leave their porch light on, or charge their phone, or keep a hospital running through the night. And the whole thing traces back to a handful of curious people who had no idea, truly no idea, what they were about to unleash. They were just trying to understand what matter was made of. That's it. They wanted to know what was inside the atom. And in poking around, they accidentally stumbled onto the most concentrated source of energy human beings have ever found. Let's start there. Let's start with the atom itself, because everything, the reactors, the fuel rods, the cooling towers, the whole chain of engineering that makes nuclear power work, all of it depends on one strange, counterintuitive fact about the universe. And that fact is this: the stuff that holds an atom's nucleus together contains an almost absurd amount of energy. Way more than you'd expect. Way more than the chemical bonds that hold molecules together, which is what we tap into when we burn coal or gas or wood. We're talking about 1,000,000 times more energy, roughly, locked inside the nucleus of a single atom compared to what you get from a chemical reaction involving that same atom. 1,000,000 times. That number is real. And figuring out that this energy existed, and then figuring out how to release it in a controlled way, that's the story we're going to walk through tonight, slowly, from the very beginning. Now, to understand how we got here, you have to go back to the late 1800s, to a time when scientists were just barely starting to crack open the question of what atoms actually were. For most of history, the atom was a philosophical idea more than a scientific one. The ancient Greeks, Democritus, around 400 BC, had proposed that if you kept cutting matter into smaller and smaller pieces, you'd eventually reach something indivisible, something that couldn't be cut any further. They called it atomos, uncuttable. And for over 2,000 years, that was more or less where things stood. Atoms were a nice idea, but nobody could see them. Nobody could measure them. And honestly, for a long time, a lot of serious scientists weren't even sure they were real. But then the 19th century happened, and chemistry started producing results that were really hard to explain without atoms. John Dalton, an English chemist working in the early 1800s, showed that elements combined in fixed, predictable ratios, one part of this to two parts of that. And the simplest explanation was that matter came in discrete little packets, atoms. By the middle of the century, the periodic table was taking shape, thanks largely to Dmitri Mendeleev in Russia, who arranged the known elements by their properties and even predicted elements that hadn't been discovered yet. The atom was becoming real. But here's the thing. Even as late as the 1890s, most scientists thought of the atom as a tiny, solid, indivisible ball, a little billiard ball of matter, the smallest possible thing. And they were about to find out just how wrong that picture was. The first crack in the billiard ball model came from a place nobody expected. In 1895, a German physicist named Wilhelm Röntgen was experimenting with cathode rays. Basically, he was running electrical current through a glass tube with most of the air pumped out of it, which was a popular thing to do in physics labs at the time. And he noticed something strange. A fluorescent screen across the room was glowing. even though it was too far away from the tube to be hit by the cathode rays themselves. Something invisible was coming out of that tube, passing through solid objects and making the screen light up. He called them X-rays because he didn't know what they were. The X was literally for unknown. And when he put his wife's hand between the tube and a photographic plate and produced an image of her bones, visible right through her flesh, the world went a little bit crazy. That image was published everywhere. It was like nothing anyone had ever seen. Now, Röntgen's X-rays were fascinating on their own, but what they really did was kick off a frenzy of investigation. If invisible rays could come out of an electrical tube, what else might be out there? And that question led almost immediately to one of the most important discoveries in the history of science. In 1896, just a year after Röntgen's announcement, a French physicist named Henri Becquerel was investigating whether certain minerals might naturally emit X-rays after being exposed to sunlight. He was working with uranium salts, compounds containing the element uranium, and his plan was to put the uranium on a photographic plate wrapped in dark paper, leave it in the sun, and see if the sunlight energized the uranium enough to produce rays that could fog the plate through the paper. Here's where it gets good. The weather in Paris that week was overcast, cloudy. Becquerel couldn't do his experiment because there wasn't enough sunlight. So he stuck the uranium and the photographic plate in a drawer and waited for better weather. A few days later, for reasons that aren't entirely clear, maybe he was just tidy, maybe he was curious, he decided to develop the photographic plate anyway, expecting to see maybe a faint image or nothing at all. Instead, the image was strong, clear. The uranium had fogged the plate while sitting in a dark drawer with no sunlight at all. The rays weren't coming from the sun's energy being re-emitted. They were coming from the uranium itself, spontaneously, all on its own. Think about what that means for a second. Here was a chunk of material, just sitting there, quietly and invisibly, sending out some kind of radiation without any external energy source. Nobody had ever seen anything like that. Where was the energy coming from? It wasn't a chemical reaction. It wasn't heat. It wasn't electricity. The uranium was just radiating. Becquerel had discovered radioactivity, though the word itself wouldn't be coined for another couple of years. And the person who coined it, who really grabbed this discovery and ran with it harder and further than anyone else, was Marie Curie. Marie Sklodowska-Curie, born in Warsaw in 1867, had come to Paris to study physics at the Sorbonne because women weren't allowed to attend university in Poland at the time. She was brilliant, driven, and working under conditions that would have stopped most people cold. She and her husband Pierre decided to investigate Becquerel's rays systematically. Marie's approach was methodical and exhausting. She tested every element she could get her hands on, measuring the radiation using an electrometer that Pierre and his brother had invented. She found that thorium was also radioactive, and then she noticed something puzzling. A uranium ore called pitch blende was more radioactive than pure uranium itself. That meant there had to be something else in the pitch blende, some unknown element, that was even more radioactive than uranium. So she set out to find it. And this is where the story becomes physically grueling in a way that's hard to overstate. The Curies worked in a converted shed, basically a leaky, unheated former dissecting room at the school where Pierre taught. They processed tons of pitch blende ore, literally tons. Marie would spend entire days stirring massive vats of boiling, chemically treated ore with an iron rod almost as tall as she was. The work was backbreaking, and at the end of it, from tons of raw material, they isolated tiny amounts of two new elements. The first they named polonium, after Marie's homeland. The second they named radium. And radium was extraordinary. It was so intensely radioactive that it glowed in the dark. A tiny vial of radium salt would sit on a shelf and emit a faint, eerie blue light, all on its own, endlessly, as if it contained some inexhaustible inner fire. The Curies won the Nobel Prize in 1903, shared with Becquerel. Marie would win a second Nobel in 1911, this time in chemistry, for her work isolating radium and polonium. She remains the only person ever to win Nobel Prizes in two different sciences. But here's the thing that haunts this story. Neither Marie nor anyone else at the time understood how dangerous this radiation was. Marie carried vials of radioactive material in her pockets. Her lab, notebooks from that era, are still so radioactive that they're kept in lead-lined boxes in France, and if you want to look at them, you have to wear protective gear and sign a liability waiver. Marie Curie died in 1934 of aplastic anemia, almost certainly caused by years of radiation exposure. She gave her life to this work in the most literal sense possible. But what she and Becquerel and the other early researchers had uncovered was the first hint that atoms were not simple, not inert, not indivisible. Something was happening inside them. Energy was leaking out. And the question that consumed the next generation of physicists was, what's in there? What is the internal structure of the atom? And where is all this energy coming from? The answer started to take shape in a laboratory in Manchester, England, around 1909, in one of the most famous experiments in the history of physics. Ernest Rutherford, a New Zealander, big personality, booming voice, the kind of guy who dominated every room he walked into, had been studying radioactivity for years. He'd already figured out that there were at least two different kinds of radiation coming from radioactive materials, which he'd named alpha and beta. Alpha particles were relatively heavy and positively charged. Beta particles were lighter and negatively charged. And Rutherford had an idea. He wanted to use alpha particles as tiny projectiles, firing them at a thin sheet of gold foil to see what happened. The prevailing model of the atom at the time, proposed by J.J. Thomson, imagined the atom as a sort of plum pudding, a diffuse blob of positive charge with negatively charged electrons scattered through it, like raisins in a pudding. If that model was right, the alpha particles should pass through the gold foil with only slight deflections, like bullets through tissue paper. And most of them did. Most of the alpha particles went straight through, but some of them, a small fraction, bounced back. They came flying back toward the source, deflected at huge angles, sometimes almost straight back the way they'd come. Rutherford later said it was as if you'd fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. It was, he said, the most incredible thing that had ever happened to him in his life. What it meant was that almost all of the atom's mass and all of its positive charge was concentrated in a tiny, dense core, what Rutherford called the nucleus. The rest of the atom was mostly empty space, with electrons orbiting far away from that central nucleus. The atom wasn't a solid ball. It wasn't plum pudding. It was more like a tiny solar system, with a dense sun at the center and planets orbiting at great distances. And that nucleus, that incredibly small, incredibly dense heart of the atom, that was where the energy was hiding. That was the lock. And physicists were just beginning to figure out the key. Now, understanding that the nucleus existed was one thing. Understanding what it was made of and why it held together and what happened when it came apart, that took another few decades of painstaking work. Rutherford himself discovered the proton in 1917, showing that the nucleus of hydrogen consisted of a single positively charged particle. But heavier elements had nuclei that were heavier than their proton count alone could explain. Something else was in there, something with mass but no electric charge. It wasn't until 1932 that James Chadwick, working in Rutherford's old lab at Cambridge, finally identified the neutron, an uncharged particle with almost the same mass as a proton, sitting right there in the nucleus alongside the protons. And the neutron, it turned out, was going to change everything. Not just because it completed our picture of the atom, but because of a very specific, very practical property it had. See, the neutron has no electric charge, and that means it isn't repelled by the positively charged nucleus the way a proton or an alpha particle would be. A neutron can just drift right up to a nucleus and walk in the front door, so to speak. No resistance, no electromagnetic barrier to overcome. And when a neutron enters a nucleus, it can destabilize it. It can make things happen. It can, under the right conditions, make the nucleus split apart. But we're getting a little ahead of ourselves, because before anyone figured out that splitting the atom was possible, a quiet, unassuming physicist in Berlin was about to perform an experiment that would baffle him so completely that he'd write to his former colleague in Sweden, convinced he'd lost his mind. And that colleague, a woman who'd been forced to flee Nazi Germany just weeks earlier, would be the one to figure out what had actually happened. She would give it a name that the whole world would soon learn to fear: fission. The woman was Lise Meitner, and her story is one of the most remarkable and, honestly, one of the most unjust in all of 20th century science. She was born in Vienna in 1878, the third of 8 children in a Jewish family. From a young age, she was fascinated by physics. But here's the thing about being a woman interested in science in turn-of-the-century Austria. The doors were mostly closed. Women weren't allowed to attend the gymnasium, the academic high school that prepared students for university. Meitner had to study privately, passing the entrance exam for the University of Vienna as an external candidate in 1901, which was itself a small act of defiance. She studied under Ludwig Boltzmann, one of the giants of statistical mechanics, and earned her doctorate in physics in 1906, only the second woman to do so at that university. She moved to Berlin in 1907 to continue her research, and this is where she met Otto Hahn, a chemist just a year older than her. They began collaborating almost immediately, and their partnership would last more than 30 years. But the conditions were absurd. The institute director, Emil Fischer, didn't allow women in the laboratories. Meitner had to work in a converted carpenter's workshop in the basement. She wasn't allowed to set foot on the upper floors where the real labs were. She wasn't paid for years. And yet she kept working, kept publishing, kept pushing the boundaries of what was understood about radioactivity. Over the decades, Meitner became one of the most respected physicists in Germany. She was the first woman to become a full professor of physics in the country at the University of Berlin. She and Hahn continued their collaboration, with Hahn handling the chemistry, separating and identifying elements, and Meitner providing the physics, interpreting what the results meant at the atomic level. They were a brilliant team, complementary in the best sense. But then the 1930s happened. The Nazis rose to power. Meitner was Austrian by birth and had converted from Judaism to Protestantism years earlier, but none of that mattered under the racial laws. For a while, her Austrian citizenship offered some protection. But in March 1938, Germany annexed Austria, and overnight Meitner became a German citizen subject to the full force of Nazi persecution. her situation became desperate. In July 1938, with the help of colleagues, notably the Dutch physicist Dirk Koster, she fled Germany with almost nothing. She carried 10 marks in her purse and a diamond ring that Max Planck had given her, just in case she needed to bribe a border guard. She made it to the Netherlands and eventually to Sweden, where she took a position at the Nobel Institute in Stockholm. It was safe, but it was isolating. She was cut off from her lab, her equipment, her life's work, and from Han. And this is exactly when things got interesting in the lab she'd left behind. See, throughout the mid-1930s, physicists across Europe had been bombarding various elements with neutrons, following up on work pioneered by Enrico Fermi in Rome. Fermi had systematically fired neutrons at element after element, working his way up the periodic table, and when he got to uranium, the heaviest naturally occurring element, he found something puzzling. The resulting radioactive products didn't seem to match any of the elements near uranium on the periodic table. Fermi thought he might have created entirely new elements heavier than uranium, transuranic elements, which would have been a spectacular discovery. And in fact, he was awarded the Nobel Prize in Physics in 1938, partly on the basis of this interpretation. But Hahn and Meitner, along with a younger chemist named Fritz Strassmann, had been trying to sort out exactly what was happening when uranium was bombarded with neutrons. The chemistry was confusing. They kept finding radioactive products that behaved like lighter elements. Radium, actinium, elements that shouldn't have been there. It didn't make sense. If you hit uranium with a neutron, you might expect to knock off a small piece, an alpha particle, maybe a proton or two. You'd get elements close to uranium on the periodic table. That was the conventional wisdom. Nobody seriously considered that the uranium nucleus might do something far more dramatic. In December 1938, with Meitner now in Sweden, Hahn and Strassmann performed a series of meticulous chemical analyses on the products of their neutron bombardment of uranium, and they found something that shook Hahn to his core. One of the products wasn't radium at all, it was barium. Barium, with an atomic number of 56. Uranium has an atomic number of 92. That's not chipping a small piece off the nucleus. That's the nucleus breaking roughly in half. Hahn couldn't believe it. As a chemist, he trusted his analysis. He was one of the best radiochemists in the world, and his identification of barium was solid. But as a scientist steeped in decades of nuclear physics, he knew this result seemed impossible. The prevailing model of the nucleus didn't predict anything like this. So he wrote to Meitner. His letter, dated December 19, 1938, is one of the most extraordinary documents in the history of science. He described his results and essentially said, "I know this can't be right, but the chemistry is telling me we've broken uranium into barium. Please help me understand what's happening." He even wrote, perhaps as a joke, perhaps not, that maybe the nucleus had burst apart. Meitner received the letter while she was visiting friends in the small Swedish town of Kungälv, near Gothenburg, over the Christmas holiday. Her nephew, Otto Robert Frisch, also a physicist, happened to be visiting at the same time. And it was there, over the holiday, that the two of them worked out what had happened. Here's where the physics gets really beautiful, so let's slow down for a moment. Think of the nucleus of a uranium atom. It's got 92 protons and, in the case of uranium-235, 143 neutrons, 235 particles crammed into an incredibly tiny space. Now, all those protons are positively charged, and positive charges repel each other. So you've got this tremendous electrostatic repulsion trying to push the nucleus apart. The only thing holding it together is the strong nuclear force, which is incredibly powerful but only works over very short distances. Essentially, each particle only feels the pull of its immediate neighbors. In a large nucleus like uranium, the protons on opposite sides are far enough apart that the strong force between them is negligible, but the electromagnetic repulsion still reaches across the whole nucleus. It's a delicate balance. The nucleus is held together, but just barely. It's like a water droplet that's trembling on the edge of breaking apart. And that's exactly the model Meitner and Frisch used. It was called the liquid drop model, originally proposed by George Gamow and later developed by Niels Bohr. The idea is that the nucleus behaves somewhat like a drop of liquid held together by surface tension, which in this analogy corresponds to the strong nuclear force. When a neutron enters a uranium-235 nucleus, it adds energy. The nucleus begins to oscillate, to wobble, stretching into an elongated shape. And if the wobble is severe enough, the drop pinches in the middle, like a water balloon being squeezed, until it splits into two smaller drops. Two smaller nuclei, two new elements. Meitner did the calculation. She used Einstein's famous equation, E equals mc squared, and worked out the energy balance. The two smaller nuclei that result from the split, the fission fragments, together have slightly less total mass than the original uranium nucleus, plus the neutron. That missing mass has been converted into energy, and the amount of energy is enormous, roughly 200 million electron volts per fission event. To put that in perspective, a chemical reaction, burning coal, say, or detonating TNT, releases energy on the order of a few electron volts per atom. Fission releases something like 50 million times more energy per atom. 50 million times. That's the number that changes everything. Frisch went back to Copenhagen, where he was working at Niels Bohr's institute, and told Bohr about the discovery. Bohr reportedly slapped his forehead and said something to the effect of, "Oh, what fools we've been! We should have seen this before." Frisch also needed a name for the process. He consulted with a biologist friend who told him that when a cell divides in two, biologists call it fission. And so Frisch borrowed the term, nuclear fission. Hahn and Strassmann published their chemistry results in January 1939. Meitner and Frisch published the physical interpretation shortly after. The news spread through the physics community with astonishing speed. Within weeks, laboratories across the world were replicating the experiment. Fission was real. But here's the thing that immediately occurred to several physicists, almost as soon as they heard the news. When a uranium nucleus splits, it doesn't just produce two large fragments and a burst of energy. It also releases additional neutrons. Typically, 2 or 3 free neutrons fly out of the fission event, and those neutrons, those uncharged nucleus-penetrating neutrons, could potentially strike other uranium nuclei and cause them to split too, which would release more neutrons, which could cause more fissions, which would release more neutrons. You see where this is going. A chain reaction. The possibility hit the physics community like a thunderbolt, and it hit at the worst possible moment in history. It was early 1939. Europe was sliding toward war. Hitler had already annexed Austria and the Sudetenland. The invasion of Poland was months away, and suddenly, physicists, many of them refugees from fascism themselves, realized that the energy locked inside the atomic nucleus might be unleashed in a weapon of almost unimaginable power. The person who thought about this most urgently, most obsessively, was a Hungarian physicist named Leo Szilard. And Szilard is one of those figures who deserves to be far more famous than he is. He was brilliant, eccentric, restless. The kind of person who lived out of hotel rooms and suitcases, who seemed to be everywhere at once, who had ideas about everything. He'd actually conceived of the nuclear chain reaction years earlier, in 1933, before fission was even discovered. He was walking through London, waiting at a traffic light on Southampton Row, and the idea just came to him that if you could find an element that, when hit by a neutron, released two neutrons, you could create a self-sustaining chain reaction. He even filed a patent on the concept and assigned it to the British Admiralty in secret, because he was already worried about the military implications. Now, in early 1939, with fission confirmed and the neutron multiplication verified experimentally, Szilard was terrified. He knew that German physicists understood fission. Hahn and Strassmann had discovered it in Berlin, for God's sake. He knew that Germany had access to uranium ore, and he knew that if the Nazis developed a fission weapon first, the consequences would be catastrophic. So Szilard did something extraordinary. He went to see Albert Einstein. Einstein was living in Princeton, New Jersey, having left Germany in 1933. He and Szilard knew each other. They'd even collaborated on a refrigerator design years earlier, which is a wonderful side note. Szilard drove out to Einstein's summer cottage on Long Island in August 1939, accompanied by another Hungarian physicist, Edward Teller, who did the driving because Szilard didn't have a car. They explained the situation to Einstein: uranium fission, chain reactions, the possibility of a bomb. Einstein, who had never worked on nuclear physics directly, grasped the implications immediately. Together, they drafted a letter to President Franklin Roosevelt. The letter, dated August 2, 1939, is measured and careful, but its message is unmistakable. It warns that recent research on uranium chain reactions could lead to the construction of extremely powerful bombs and urges the government to take action. Einstein signed it. The letter was delivered to Roosevelt in October 1939, about a month after Germany invaded Poland and World War II began in Europe. Roosevelt's response was to form an advisory committee, the Advisory Committee on Uranium, sometimes called the Briggs Committee, after its chairman, Lyman Briggs. And here's where you might expect the story to accelerate, but actually, things moved frustratingly slowly at first. The committee met, discussed, allocated a modest sum, $6,000, for research into graphite as a potential neutron moderator. $6,000 to investigate what might become the most powerful weapon in human history. The urgency that Szilard felt, that bone-deep fear of a German bomb, hadn't yet translated into government action at any meaningful scale. But across the Atlantic, something was happening that would eventually change the calculus entirely. In early 1940, two refugee physicists working at the University of Birmingham in England, Rudolf Peierls and Otto Frisch, the same Frisch who'd named fission, sat down and did a calculation that nobody else had bothered to do carefully. They asked a simple question: how much uranium-235 would you actually need to sustain an explosive chain reaction? The prevailing assumption was that you'd need tons of the stuff, which made a bomb seem impractical. But Peierls and Frisch realized that if you used pure uranium-235, separated from the far more common uranium-238, the critical mass was much, much smaller than anyone had guessed. Their estimate was about 1 kilogram. The actual number turned out to be larger, around 15 kilograms for a bare sphere, but the point was the same. A fission bomb was not a theoretical fantasy requiring impossible quantities of material. It was, in principle, buildable. And the memorandum they wrote, the Frisch-Peierls Memorandum of March 1940, laid it out with chilling clarity. They described not just the physics, but the likely effects. The blast, the heat, the radioactive fallout that would make the area dangerous for a long time afterward. They were brutally honest about what this weapon would do. And that honesty is what made the memorandum so effective, because it didn't read like science fiction. It read like an engineering assessment. Here is what we can build. Here is what it will do. And here is why you need to take this seriously right now. The memorandum landed on the desk of Mark Oliphant, an Australian physicist working in Birmingham, and he made sure it reached the right people in the British government. Within months, Britain had established a secret committee with the deliberately bland code name MAUD, which, by the way, came from a garbled telegram Niels Bohr sent from occupied Denmark that ended with the words "Tell Cockcroft and Maud Ray Kent," and everyone assumed Maud Ray Kent was some kind of anagram or code. It wasn't. Maud Ray was actually the name of a former governess who'd looked after Bohr's children and lived in Kent. But the name stuck, and the Maud Committee became one of the most important scientific advisory bodies of the war. The Maud Committee did something the American Briggs Committee hadn't managed to do. It moved fast. Over the course of about a year, from April 1940 to July 1941, the committee gathered Britain's best physicists and had them work through every major question. Could you actually separate enough uranium-235 from natural uranium to build a bomb? What methods might work? How long would it take? How much would it cost? And their final report, delivered in July 1941, was unequivocal. A uranium bomb was feasible. It could be built within roughly 2 years. It would likely use about 10 kilograms of uranium-235, and the report recommended, in the strongest possible terms, that work should proceed immediately. Now, here's what's really important about the MAUD report. It crossed the Atlantic. Oliphant, frustrated that the Americans still seemed to be dragging their feet, actually flew to the United States in August 1941 and personally lobbied American scientists and officials. He discovered that Lyman Briggs had received a copy of the Maud report and had apparently locked it in a safe without showing it to key members of his own committee. Oliphant was furious. He went directly to people like Ernest Lawrence at Berkeley, Arthur Compton at Chicago, and others, essentially shaming the American scientific establishment into action. And it worked. By October 1941, the National Academy of Sciences delivered its own report to Roosevelt, confirming the MAUD Committee's conclusions, and Roosevelt authorized a full-scale effort. Then, of course, December 7, 1941, Pearl Harbor, and suddenly the United States was at war, and everything accelerated. By the summer of 1942, the effort had been placed under the Army Corps of Engineers, and in September of that year, a 46-year-old Army colonel named Leslie Groves was promoted to brigadier general and put in charge. Groves was an interesting choice. He was an engineer by training. He'd just overseen the construction of the Pentagon, which gives you a sense of the scale of projects he was used to managing. He was brusque, demanding, overweight, and absolutely relentless. Scientists often found him difficult. He found scientists exasperating, but he got things done. And that was exactly what was needed, because the Manhattan Project, as it came to be called, was not primarily a physics problem anymore. The physics was known. What remained was an engineering problem of staggering complexity. Think about what they actually had to do. They needed to produce enough fissile material, either uranium-235 or this new element, plutonium, which had been discovered in 1941 by Glenn Seaborg's team at Berkeley, to build a weapon. And producing that material required entirely new industrial processes that had never been attempted at any scale, let alone the scale needed for a war effort. Let's start with uranium-235, because the challenge here is almost absurdly difficult, and understanding it helps you appreciate just how much engineering muscle went into this project. Natural uranium is about 99.3% uranium-238, and only about 0.7% uranium-235. Those two isotopes are chemically identical. They're both uranium. They behave the same way in chemical reactions. The only difference is that uranium-235 has 3 fewer neutrons in its nucleus, which makes it very slightly lighter, so you can't separate them chemically. You have to exploit that tiny mass difference, and that's incredibly hard to do. Several methods were pursued simultaneously because nobody knew which one would work best, and there wasn't time to try them sequentially. One approach was gaseous diffusion. The idea is that you convert uranium into a gas, uranium hexafluoride, a nasty corrosive compound, and then push that gas through a barrier with microscopic pores. The lighter molecules, the ones containing uranium-235, diffuse through the barrier very slightly faster than the heavier uranium-238 molecules. But the enrichment you get from a single pass through one barrier is minuscule. We're talking about a separation factor of something like 1.0043. Essentially nothing. So you have to cascade the process, take the slightly enriched gas from one stage, feed it into the next, and repeat this thousands of times. The gaseous diffusion plant built at Oak Ridge, Tennessee, called K25, was at the time the largest building in the world under one roof. It was U-shaped, half a mile long, and contained thousands of diffusion stages with miles and miles of piping, all of which had to be absolutely leak-tight because uranium hexafluoride is ferociously corrosive and reacts with moisture in the air. The engineering challenges were enormous. They had to develop entirely new seals, new barrier materials, new pumps that could handle this corrosive gas without contaminating the product. And all of this was being designed and built simultaneously, often before the research was even finished. Another method was electromagnetic separation, championed by Ernest Lawrence, who'd invented the cyclotron. The idea was essentially a giant mass spectrometer. You ionize uranium atoms, accelerate them through a magnetic field, and because the lighter uranium-235 ions curve along a slightly tighter path than the heavier uranium-238 ions, they land at slightly different spots, and you can collect them separately. Lawrence's devices, called calutrons, were built at Oak Ridge in a facility called Y12. These machines used enormous magnets, so enormous that they required thousands of tons of silver borrowed from the U.S. Treasury because there wasn't enough copper available during wartime. 14,700 tons of silver formed into electrical conductors for the magnets. The Treasury Department tracked every ounce and wanted it all back after the war, which they eventually got. The calutrons worked, but they were slow and inefficient. They consumed enormous amounts of electricity. And here's a detail that always strikes me. The calutrons were largely operated by young women from rural Tennessee, recruited because they were available and could be trained to monitor the equipment. These operators, most of whom had no idea what they were actually producing, turned out to be better at running the machines than the PhD physicists because the scientists kept trying to optimize and adjust things, while the operators simply followed instructions precisely and consistently. There's a lesson in there somewhere about the difference between understanding a system and operating one. And then there was plutonium. This was the other path to a bomb, and in some ways it was even more remarkable. Plutonium doesn't exist in nature in any meaningful quantity. It had to be manufactured, atom by atom, inside a nuclear reactor. The idea was straightforward in principle. You put natural uranium in a reactor, sustain a controlled chain reaction, and some of the uranium-238 atoms absorb neutrons and, through a series of radioactive decays, transform into plutonium-239, which is fissile. Then you chemically separate the plutonium from the uranium and the intensely radioactive fission products. But to do this, you first needed a working nuclear reactor. And that brings us to one of the most remarkable moments in the entire story. December 2nd, 1942, under the bleachers of the squash court at Stagg Field, the University of Chicago. Enrico Fermi, the Italian physicist who'd fled Mussolini's fascist Italy in 1938, had been building what he called a pile, layers of uranium metal and uranium oxide interspersed with blocks of ultra-pure graphite, which served as a moderator to slow down the neutrons. The whole structure was roughly 25 feet wide and 20 feet high, an oblate spheroid shape, and it contained about 50 tons of uranium and nearly 400 tons of graphite. There was no radiation shielding to speak of. There was no containment building. It was built in the middle of a major city, under a football stadium. The safety measures consisted of cadmium control rods that absorbed neutrons. You pulled them out to let the reaction intensify, pushed them in to slow it down, and a so-called suicide squad standing on top of the pile with jugs of cadmium sulfate solution to pour over the reactor if everything went wrong. On that December afternoon, Fermi directed the gradual withdrawal of the control rods, watching the neutron counters climb. The key measurement was the multiplication factor, the ratio of neutrons in one generation to the next. When it reached exactly 1, the reactor would be critical, sustaining a steady chain reaction. Fermi, with his legendary ability to do calculations in his head, monitored the instruments calmly, predicting each reading before it appeared. At about 2:30 in the afternoon, the last control rod was pulled out to the calculated position, and the neutron intensity began to rise, not exponentially out of control, but steadily in a self-sustaining chain reaction. Fermi let it run for about 28 minutes, then ordered the control rods reinserted. The power output was tiny, about half a watt, barely enough to light a flashlight bulb. But the principle was proven. A controlled, self-sustaining nuclear chain reaction was real. Arthur Compton, who was overseeing the project from Chicago, made a famous phone call to James Conant at the National Defense Research Committee. "The Italian navigator has just landed in the New World," Compton said. Conant asked, "How were the natives?" And Compton replied, very friendly. It was coded language, but the meaning was clear. Fermi's pile worked. Now, a half-watt reactor under a squash court is a very long way from an industrial plutonium production facility. Scaling up required solving problems that Fermi's Chicago pile didn't even have to face. You needed much higher power levels to produce meaningful quantities of plutonium, which meant you needed to remove enormous amounts of heat, which meant you needed a cooling system. You needed thick biological shielding to protect workers from the intense radiation. You needed a way to load and unload uranium fuel. And you needed to do all of this reliably and safely, at a scale that had never been attempted. The man Groves chose to design and build these production reactors was the DuPont company. Yes, the chemical company. And the DuPont engineers, who knew nothing about nuclear physics, but knew a great deal about building large industrial plants safely, made a decision that turned out to be crucial. When the physicists at Chicago designed the production reactor for the Hanford site in Washington state, they calculated that it needed 1,500 fuel channels. The DuPont engineers, exercising what they called engineering conservatism, insisted on adding extra channels, bringing the total to 2,004. The physicists thought this was wasteful and unnecessary. But when the first Hanford reactor, called B reactor, went critical in September 1944, something unexpected happened. It started up fine, ran for a few hours, and then the power output began to drop. The chain reaction was dying, and nobody knew why. Fermi quickly figured out that a fission product, xenon-135 it turned out, was accumulating in the fuel and absorbing neutrons so effectively that it was poisoning the reaction. This was a phenomenon that hadn't been predicted, and the only reason they were able to overcome it was those extra fuel channels that DuPont had insisted on. By loading uranium into the additional channels, they could increase the reactivity enough to overwhelm the xenon poisoning. If they'd built the reactor with only 1,500 channels, as the physicists had specified, the Hanford reactors might have been useless. Engineering conservatism, building in margin for the things you don't know, saved the entire plutonium production program. And that's a theme you'll see over and over again in nuclear engineering. This tension between the physicists who understand the theory and the engineers who understand what happens when theory meets the real world. Because in the real world, materials corrode, welds crack, instruments drift, and isotopes you've never heard of show up and absorb neutrons you didn't budget for. That's just how it goes. And nowhere was this collision between elegant theory and messy reality more dramatic than at a place called Los Alamos, up on a remote mesa in northern New Mexico, where the actual bomb was being designed. See, the Manhattan Project had these parallel tracks running simultaneously. Oak Ridge was separating uranium-235. Hanford was breeding plutonium-239. But both of those were just producing the raw material, the fissile stuff. Somebody still had to figure out how to actually make that material explode. Not just undergo fission, not just sustain a chain reaction, but detonate, release an enormous amount of energy in the shortest possible time. And that problem, the weapon design problem, was centered at a secret laboratory that Groves established in the spring of 1943 on the site of a former boys' ranch school in the mountains northwest of Santa Fe. The scientific director was J. Robert Oppenheimer. Now, Oppenheimer is one of those figures who's so layered, so contradictory, that you could spend hours just talking about him. He was tall, thin, chain-smoked, spoke 6 languages, read Sanskrit for fun, and had a kind of magnetic charisma that drew brilliant people into his orbit. He wasn't the best physicist in the world. He knew that, and the people around him knew that. He'd never won a Nobel Prize. But he had something arguably more valuable for this particular job. He could understand what everybody else was doing. He could talk to the theorists and the experimentalists and the chemists and the metallurgists and the explosives experts. And he could see how all their pieces fit together. Groves, who was a hard-nosed military man with very little patience for academic egos, recognized this quality immediately. The two of them made an unlikely pair, the gaunt, poetic physicist and the blunt, overweight Army engineer. But their partnership worked. So here's the core problem they faced at Los Alamos. You've got your fissile material, let's say uranium-235. You know that if you assemble enough of it in one place, more than the critical mass, a chain reaction will start and grow exponentially. Each fission releases neutrons. Those neutrons cause more fissions, and the energy output doubles and doubles and doubles in microseconds. But here's the thing. As soon as the chain reaction starts generating serious energy, That energy wants to blow the material apart. And the instant the material flies apart, it drops below critical mass, and the chain reaction stops. So you're in a race. You need the chain reaction to proceed through as many generations as possible before the material disassembles itself. The more generations of fission you get, the bigger the explosion. If the material comes apart too early, what they called a fizzle, you get a much smaller yield. Still a nasty radioactive mess, but not the city-destroying weapon they were trying to build. Think about it this way. Imagine you're trying to light a bonfire, but the logs are on springs, and they're going to fly apart the moment they get hot. You need to get the fire going so fast, so intensely, that by the time the logs start moving, most of the wood has already burned. That's essentially the challenge. You need to assemble the critical mass and keep it together long enough for the chain reaction to do its work. And long enough in this context means something like a microsecond, a millionth of a second. The simplest approach, and the one they thought of first, was the gun-type design. The idea is beautifully straightforward. You take a subcritical piece of uranium-235 and you fire it down a gun barrel into another subcritical piece. When they slam together, the combined mass is supercritical, and the chain reaction takes off. It's basically an artillery piece. You're using conventional explosives, cordite, gunpowder, to propel one chunk of fissile material into another at high speed. The design was called Thin Man initially, later shortened to Little Boy, and it was so conceptually simple that the Los Alamos scientists were fairly confident it would work without even being tested. You just had to make sure the two pieces came together fast enough that the chain reaction didn't start prematurely and blow them apart before full assembly. For uranium-235, this was achievable. The rate of spontaneous neutron emission in U-235 is low enough that you have a reasonable window to get the pieces together before a stray neutron sets things off too early. But here's where it gets really interesting. They originally planned to use the gun-type design for plutonium as well. Makes sense, right? Same basic principle. Shoot one piece into another. Simple, reliable, done. Except in the summer of 1944, a physicist named Emilio Segre, who'd been doing careful measurements on the plutonium coming out of the Hanford reactors, discovered something deeply troubling. The reactor-produced plutonium contained a significant fraction of plutonium-240, an isotope that hadn't been present in the tiny samples they'd been working with from cyclotrons. And plutonium-240 has a spontaneous fission rate that is enormously higher than plutonium-239. What that means is that it's constantly spitting out neutrons on its own without being hit by anything. And the rate is so high that in a gun-type assembly, where the two pieces take maybe a millisecond to come together, there would almost certainly be a stray neutron that would initiate the chain reaction before the pieces were fully assembled. You'd get a fizzle, a premature detonation. The yield might be a few hundred tons of TNT equivalent instead of thousands. Still devastating, but a strategic failure. This was a crisis, a genuine crisis, because the Hanford reactors were producing plutonium specifically for weapons, and now it looked like that plutonium couldn't be used in the straightforward gun-type design. Months of work, billions of dollars, an entire city of workers at Hanford, and the product might be unusable in the only weapon design they were confident about. So they had to pivot, and the pivot was implosion. Now, the implosion concept had been floating around Los Alamos almost from the beginning. Seth Nettermeyer, a quiet, somewhat stubborn physicist, had been experimenting with it since 1943. The idea is this. Instead of shooting two pieces together in a line, you take a single sphere of plutonium, subcritical at normal density, and you surround it with conventional explosives. You detonate all the explosives simultaneously, and the resulting shockwave compresses the plutonium sphere inward, squeezing it to a higher density. And here's the key insight. Critical mass depends on density. If you can compress the plutonium to twice its normal density, the critical mass drops dramatically. So a piece that was subcritical at normal density becomes supercritical when compressed. And because the compression happens from all sides simultaneously, the assembly is extremely fast, much faster than a gun-type design. Fast enough to beat the spontaneous neutrons from plutonium-240. Beautiful idea, incredibly difficult to actually do. The problem is symmetry. You need the implosion to be perfectly spherical. If the shockwave is even slightly uneven, if one part of the plutonium gets squeezed a little more than another, you get jets and instabilities, and instead of a smooth compression, you get a mess. The plutonium squirts out through the weak spots, and you don't achieve the density you need. Think about trying to squeeze a ball of clay by pressing on it from all directions with your hands. If your hands aren't perfectly coordinated, the clay bulges out between your fingers. Now imagine you need that compression to be uniform to within a few percent, and it has to happen in microseconds. That's the implosion problem. Neddermeyer's early experiments were not encouraging. He was wrapping metal cylinders with explosives and trying to compress them symmetrically, and the results were lumpy and uneven. Oppenheimer, recognizing that this was now the critical path for the plutonium weapon, brought in a new person to take over the implosion effort in the fall of 1943, George Kistiakowsky, a Ukrainian-born chemist who was one of the world's leading experts on explosives. Kistiakowsky and Neddermeyer clashed almost immediately. Neddermeyer was methodical, a loner, and he resented being sidelined. Kistiakowsky was brash, confident, and used to running large teams. It was messy, personally and professionally. But Kistiakowsky brought something essential. He understood that the key to a symmetrical implosion was something called explosive lenses. Here's how explosive lenses work, and this is genuinely clever. Different explosive compositions detonate at different velocities. A fast explosive might have a detonation velocity of 8,000 meters per second, while a slower one might run at maybe 5,000. Kistiakowsky's team realized that by carefully shaping blocks of fast and slow explosives and fitting them together, like the panels on a soccer ball, they could manipulate the shape of the detonation wave. The fast explosive would race ahead in some regions, while the slow explosive lagged in others, and by choosing the geometry precisely, you could take an initially irregular detonation front and reshape it into a perfectly converging sphere. It's exactly analogous to how a glass lens bends light. A lens works because light travels at different speeds in glass versus air, and the curved shape converts a flat wave of light into a converging one. Same principle, but with detonation waves instead of light, and with high explosives instead of glass. Getting this right required extraordinary precision. The explosive lens components had to be cast and machined to tight tolerances. Each lens had to fit perfectly against its neighbors. The detonators, 32 of them arranged around the sphere, had to fire within a microsecond of each other. If even one was late, the symmetry would be ruined. The electronics to achieve this simultaneous detonation were designed by a group led by Luis Alvarez, who would later win a Nobel Prize for particle physics, but who spent the war years building detonator circuits. And at the very center of this converging explosive sphere sat the plutonium core. They called it the pit, a sphere of plutonium about the size of a grapefruit, warm to the touch from its own radioactive decay. Surrounding the pit was a shell of natural uranium called the tamper, which served two purposes. Its inertia helped hold the compressed core together for a few extra fractions of a microsecond, giving the chain reaction more time to proceed, and it also reflected neutrons back into the core, reducing the amount of plutonium needed. And nestled right at the very center of the pit was a small device called the initiator, a little sphere of beryllium and polonium, designed so that when the implosion compressed it, the two materials would mix and produce a burst of neutrons at exactly the right moment to kickstart the chain reaction. The whole assembly was a masterpiece of engineering coordination. Explosives, metallurgy, electronics, nuclear physics, all interlocking with microsecond timing. And unlike the uranium gun-type bomb, nobody was confident it would work without a test. There were too many things that could go wrong, too many variables that couldn't be fully calculated, which is why, on July 16, 1945, in the desert of southern New Mexico at a site called Trinity, they gathered to find out. The device they placed atop a 100-foot steel tower was called the Gadget. Not a bomb in the military sense. It had no casing designed for aerodynamic drop, no fusing for an aircraft release. It was a physics experiment, the most expensive and consequential physics experiment in human history, and the scientists and engineers who had built it were genuinely uncertain about the outcome. Edward Teller was worried it might ignite the atmosphere. Enrico Fermi, in his characteristic way, was taking side bets on whether it would destroy all of New Mexico or just the immediate area, half joking, half not, and either way, making the military officers around him extremely nervous. The weather that night was terrible. Thunderstorms rolled across the Jornada del Muerto. That's the name of the desert basin, and it translates to Journey of the Dead Man, which feels almost too on the nose. Rain lashed the tower. Lightning crackled nearby. And you have to imagine the anxiety of the people responsible for all those electrical detonator circuits sitting up there in the storm. The test had been scheduled for 4 a.m, but Groves and Oppenheimer delayed it, waiting for the weather to clear. Oppenheimer was chain-smoking, gaunt, exhausted. Groves was stoic but privately furious at the sky. The meteorologist, a man named Jack Hubbard, kept promising the storms would pass, and people's careers hung on whether he was right. Around 5:10 a.m, the skies began to clear enough. The countdown proceeded, and at exactly 5:29 and 45 seconds on the morning of July 16, 1945, the firing circuit sent its signal. 32 detonators fired within a microsecond of each other. The explosive lenses shaped their converging shockwave. The plutonium core was squeezed from a subcritical arrangement into a supercritical one. The initiator released its burst of neutrons, and in roughly 1 microsecond, 1/1,000,000th of a second, the chain reaction ran through about 80 generations of fission, releasing energy equivalent to about 21,000 tons of TNT. The flash was visible from 150 miles away. The fireball vaporized the steel tower completely, not melted, vaporized. The desert sand beneath the tower was fused into a glassy, slightly radioactive substance they later called trinitite, a greenish glaze coating the desert floor for hundreds of yards in every direction. The mushroom cloud rose to over 40,000 feet. At the base camp 10 miles away, the blast wave hit like a physical punch. Fermi had prepared one of his famous quick estimates. He dropped small pieces of paper before, during, and after the blast wave passed and measured how far they were displaced. From that, he estimated the yield at about 10 kilotons. He was in the right ballpark, which is remarkable given his method was literally dropping scraps of paper in the desert wind. The reactions of the people who witnessed it are some of the most documented emotional responses in the history of science. Oppenheimer later said he thought of a line from the Bhagavad Gita, "Now I am become death, the destroyer of worlds." Kenneth Bainbridge, the test director, turned to Oppenheimer and said something more blunt. "Now we are all sons of bitches." Some people cheered, some wept, some were simply silent. Isidore Rabi, who watched from a distance, said the experience made him suddenly feel the skin on his hands, as if he could feel the equilibrium of the forces holding his own body together, and he didn't like the feeling. And here's what I want you to sit with for a moment. Everything that led to this flash in the New Mexico desert, the decades of patient physics, the discovery of the neutron, fission, chain reactions, the industrial might of Oak Ridge and Hanford, the theoretical brilliance of Los Alamos, all of it converged into a single microsecond of confirmation. The implosion design worked, the physics was right, and the world changed. 3 weeks later, on August 6, 1945, a B-29 called the Enola Gay dropped Little Boy, the uranium gun-type bomb, the simpler design that didn't need testing, on Hiroshima. 3 days after that, on August 9th, a second B-29 called Boxcar dropped Fat Man, an implosion device essentially identical to the gadget, on Nagasaki. The combined death toll, immediate and from radiation injuries in the following weeks, was somewhere around 200,000 people. Japan surrendered on August 15th. The war was over. Now, I want to be careful here, because this is where the story of nuclear weapons and the story of nuclear power begin to diverge, and it's important to understand that divergence clearly. Everything we've talked about so far, the Manhattan Project, the chain reaction, the bomb, was about releasing nuclear energy as fast as possible in the most uncontrolled way imaginable. The entire engineering challenge was to hold a supercritical mass together long enough for the maximum number of fission generations to occur before the thing blew itself apart. Speed was everything. Containment was the enemy. Nuclear power is the exact opposite problem. In a nuclear reactor, you want the chain reaction to proceed, yes, but slowly, steadily, under precise control, generating heat at a rate you can manage and convert into useful work. If the bomb is an explosion, the reactor is a campfire. Same underlying physics, fission of heavy nuclei releasing energy and neutrons, but completely different engineering philosophy. And the fascinating thing is that the people who built the bombs understood this distinction from the very beginning. Even during the Manhattan Project, even while racing to build weapons, some of the physicists were already thinking about reactors for power generation. Remember Fermi's CP1, the pile under the squash courts at the University of Chicago? That was, in a sense, the world's first nuclear reactor, even though it produced almost no usable energy, only about half a watt of heat, barely enough to feel on your hand. But the principle was there. You assemble enough fissile material in the right geometry, you moderate the neutrons to the right energy, and you get a self-sustaining chain reaction. Fermi controlled it with cadmium rods. Push them in, they absorb neutrons, and the reaction slows down. Pull them out, more neutrons are available, and the reaction speeds up. That basic control mechanism, incredibly, is still the foundation of how every nuclear reactor on Earth is controlled today. The materials have gotten better, The engineering has gotten vastly more sophisticated, but the core idea, insertable neutron-absorbing control rods, goes straight back to December 1942 in that Chicago squash court. So how do you get from a controlled chain reaction to electricity? Let's walk through that, because it's actually beautifully straightforward in concept, even though the engineering details are enormously complex. Here's the basic idea. When a uranium-235 atom fissions, it splits into two smaller atoms, fission products, plus 2 or 3 neutrons, plus energy. Most of that energy, about 80% of it, shows up as kinetic energy of those fission products. They're heavy charged particles flying apart at enormous speed, and they don't get very far. They slam into the surrounding fuel material within a fraction of a millimeter and stop. And when they stop, their kinetic energy converts to heat. That's it. That's the fundamental energy conversion in a nuclear reactor. Fission produces fast-moving fragments. Fragments stop in the fuel. Fuel gets hot. It's not mysterious. It's not exotic. It's the same basic principle as rubbing your hands together to warm them up, just at an atomic scale and with enormously more energy per event. Now, once you have hot fuel, you need to get that heat out and do something useful with it. And this is where nuclear engineering really becomes its own discipline, separate from nuclear physics. The physics tells you how to sustain the chain reaction. The engineering tells you how to safely extract the heat, convert it to electricity, and keep everything from melting, corroding, cracking, or leaking for decades of continuous operation. The most common approach, and the one that powers the majority of the world's nuclear plants today, is conceptually identical to how a coal plant or a natural gas plant works. You use the heat to boil water, you use the steam to spin a turbine, and the turbine drives a generator that produces electricity. That's it. A nuclear power plant is, at its heart, a very fancy steam engine. The nuclear part is just the heat source. Instead of burning coal or gas to boil water, you use fission. Everything downstream of the heat, the steam, the turbines, the generators, the electrical grid connection, is conventional power engineering that would be familiar to any engineer from the 1920s. But here's what makes the nuclear heat source so special, and why people got so excited about it in the late 1940s and 1950s. The energy density is almost incomprehensible. A single kilogram of natural uranium, if you could fission all of it, which you can't in practice, but bear with me, contains about as much energy as roughly 2,700 tons of coal. Let me say that again. 1 kilogram versus 2,700 tons. That's not a small difference. That's a difference so vast that it changes the fundamental economics and logistics of energy production. A coal plant needs trainloads of fuel arriving constantly. A nuclear plant can run for a year or more on a single fuel loading. For the Navy, which was one of the earliest adopters, this meant a submarine that never needed to surface for fuel. For a country worried about energy independence, it meant freedom from coal mines and oil imports. The promise was extraordinary, and the person who arguably did more than anyone to turn that promise into engineering reality was an intense, brilliant, abrasive, and absolutely relentless Navy captain named Hyman G. Rickover. If Oppenheimer was the poetic soul of the bomb, Rickover was the iron will of the reactor. And his story is one of the most remarkable in all of 20th century engineering, because he essentially willed an entire technology into existence through sheer force of personality, bureaucratic cunning, and an almost pathological refusal to accept anything less than perfection from the people who worked for him. Rickover was born in 1900 in a small town in what was then the Russian Empire, modern-day Poland. His family emigrated to the United States when he was 6, settling in Chicago. He went to the Naval Academy, graduated in 1922, and spent the next 2 decades as a competent but not particularly distinguished naval officer. He served on submarines, on surface ships, did a stint at the Bureau of Engineering. What set him apart wasn't combat heroism or social grace. By all accounts, he was prickly, impatient, and had little tolerance for what he considered incompetence, which was most things. What set him apart was his engineering mind. He understood machines, he understood systems, and he understood, with a clarity that few others possessed in the late 1940s, that nuclear energy could transform naval propulsion. In 1946, Rickover was sent to Oak Ridge as part of a small group of Navy officers and engineers to learn about nuclear technology. And something clicked. He saw immediately that a nuclear reactor could power a submarine, not just theoretically, but practically, if someone was willing to solve the engineering problems with sufficient rigor. The existing reactors were research tools built for physics experiments. They leaked. They were unreliable. They required constant tinkering by PhD physicists. What Rickover envisioned was something entirely different, a reactor that could operate continuously for years, maintained by trained enlisted sailors in the most demanding environment imaginable, sealed inside a submarine hull, hundreds of feet underwater, where a failure didn't mean a shutdown and a repair crew. It meant death. It meant the potential loss of every soul on board. So Rickover set about building something that had never existed before. And the way he did it tells you everything about why some technologies succeed and others stall out for decades. It wasn't just about physics. The physics, in a sense, was already understood. It was about engineering culture, about creating an organization that refused to cut corners, that tested everything twice and then tested it again, and that held every single person in the chain accountable for the quality of their work. Rickover didn't just build a reactor. He built a system for building reactors. And that system would go on to shape civilian nuclear power in ways that are still visible today. But first, he had to fight the bureaucracy. And this is one of those stories where you realize that some of the hardest problems in engineering aren't technical at all. They're political. In the late 1940s, nuclear energy was controlled by the newly created Atomic Energy Commission, the AEC. The Navy wanted nuclear propulsion, but the AEC controlled all fissile material, all reactor research, all the facilities. And the AEC was primarily interested in weapons production and basic research, not in building power plants for submarines. Meanwhile, within the Navy itself, there was no clear institutional home for nuclear propulsion. Rickover was a captain, not an admiral, and he didn't have the rank or the formal authority to run a major program. What he had was conviction, an encyclopedic understanding of the technical challenges, and an almost supernatural ability to work the levers of Washington. Here's what he did, and it's genuinely clever. He got himself appointed to a position in both organizations simultaneously. He became head of the nuclear power branch within the Bureau of Ships in the Navy, and he also got himself named head of the Naval Reactors branch within the AEC. Same person, 2 hats. When the Navy asked what the AEC was doing about naval reactors, Rickover answered. When the AEC asked what the Navy wanted, Rickover answered. He was essentially negotiating with himself across 2 bureaucracies, and he used that dual position to cut through the kind of interagency paralysis that kills programs before they start. It was bureaucratic judo of the highest order. By 1948, He had authorization to develop a submarine reactor. And now the real engineering began. The fundamental challenge was this: you need a reactor that's small enough to fit inside a submarine hull, powerful enough to drive the boat at high speed, and reliable enough to operate for extended periods without maintenance. The research reactors that existed at the time were enormous, fragile things. They used graphite as a moderator. Remember, the moderator is the material that slows down neutrons, so they're more likely to cause fission. Graphite works. Fermi proved that with CP1, but graphite reactors are big. They need large volumes of graphite to do the job. That's fine for a facility on land, but you can't fit that inside a submarine. Rickover's team made a critical decision early on. They would use pressurized water as both the coolant and the moderator. This is worth pausing on, because it's the design choice that would come to dominate the entire global nuclear power industry. Think about what water does in this system. First, it moderates. Ordinary water, plain old H2O, is actually a decent neutron moderator because hydrogen atoms are almost exactly the same mass as neutrons. So when a neutron collides with a hydrogen nucleus, it transfers a lot of its kinetic energy, like a billiard ball hitting another billiard ball of the same weight. The neutron slows down efficiently. Second, water carries heat away from the fuel. The fuel rods are immersed in water. The fission reactions heat the fuel. The fuel heats the water, and you pump that hot water somewhere useful. But here's the engineering problem. At normal atmospheric pressure, water boils at 100 degrees Celsius, and you want your reactor operating at much higher temperatures than that, because higher temperatures mean more efficient energy conversion. That's basic thermodynamics. If you let the water boil inside the reactor, you get steam bubbles, and those bubbles change the moderation characteristics in ways that make the reactor harder to control. So Rickover's team pressurized the water. By keeping the water under very high pressure, about 150 atmospheres, roughly 2,000 pounds per square inch, you can heat it to over 300 degrees Celsius without it boiling. The water stays liquid, stays dense, keeps moderating neutrons predictably, and carries an enormous amount of thermal energy. Then you run that superheated pressurized water through a heat exchanger, a device where the hot water from the reactor passes through tubes, surrounded by a separate water supply at lower pressure. The heat transfers through the tube walls, and the lower pressure water boils into steam. That steam drives a turbine. The turbine spins a shaft, and in a submarine, that shaft turns the propeller. In a power plant on land, that shaft turns a generator. Same principle either way. And notice something important. The water that actually touches the reactor fuel never leaves the primary loop. It circulates in a sealed system. The steam that drives the turbine comes from a completely separate secondary loop. This means the turbine and the rest of the power conversion equipment never come into contact with radioactive water. That's a safety feature, and it's elegant. The team Rickover assembled to make this work was based primarily at the Bettis Atomic Power Laboratory near Pittsburgh, operated by Westinghouse, and Rickover drove them relentlessly. He had a management style that was, to put it diplomatically, intense. He personally interviewed every officer who would serve in the nuclear navy, a practice he continued for decades, conducting thousands of interviews. These interviews were legendary. He would ask impossible questions, berate candidates, tip them out of chairs with shortened front legs, do anything to see how they handled pressure and whether they really understood the material or were just reciting memorized answers. He wanted people who thought for themselves and who would never, ever sign off on something they didn't fully understand. This culture of accountability became the backbone of what's known as naval reactors, and it's arguably the most successful nuclear safety organization in history. The United States Navy has operated hundreds of nuclear reactors on submarines and aircraft carriers since the 1950s, and it has never had a reactor accident that released significant radiation. Think about that. These are reactors operating inside sealed metal tubes that dive to crushing depths, that get tossed around by ocean swells, that undergo rapid power changes when the captain orders full speed, and the safety record is essentially perfect. That didn't happen by accident. It happened because Rickover built an organization where every procedure was documented, every deviation was investigated, and every person in the chain understood that they were personally responsible for nuclear safety. No passing the buck. No assuming someone else checked it. The first submarine reactor prototype, called S-1W, was built not in a submarine, but on land, in the Idaho desert, at what's now the Idaho National Laboratory. And here's a detail that shows you how thorough Rickover was. They built the prototype inside a submarine hull section, a full-size replica of the engine compartment of a submarine, sitting in the middle of the desert, so that every pipe routing, every valve placement, every maintenance access path could be tested exactly as it would be in the real boat. When they fired up that prototype in 1953, it worked. It ran, it produced power, and it proved that a pressurized water reactor could be made compact and reliable enough for naval service. The actual submarine, USS Nautilus, SSN 571, was launched in January 1954 and went to sea under nuclear power on January 17, 1955. And it immediately changed everything. Conventional submarines of that era were really surface ships that could submerge temporarily. They ran on diesel engines on the surface and switched to battery power underwater, and those batteries gave them maybe a few hours at modest speed before they had to surface again to recharge. Nautilus could stay submerged indefinitely. Its only limitation was food for the crew. In 1958, Nautilus made the first submerged transit of the North Pole, traveling under the Arctic ice cap, a voyage that would have been absolutely impossible for a conventional submarine. The strategic implications were enormous, and every major navy in the world took notice. But here's where the story connects back to the power plants that generate about 10% of the world's electricity today. Because the pressurized water reactor that Rickover's team developed for submarines became the template for civilian nuclear power. The logic was straightforward. If you can build a reactor that works inside a submarine, you can certainly build a larger version on land to generate electricity. And that's essentially what happened. Westinghouse, which had built the naval reactors, adapted the design for the first commercial pressurized water reactor at Shippingport, Pennsylvania, which went critical in 1957. Rickover himself oversaw the Shippingport project. It was a joint Navy AEC effort, and he ran it with the same demanding standards he applied to naval reactors. Shippingport was modest by later standards, about 60 megawatts of electrical output, but it proved the concept. A nuclear reactor could safely and reliably generate electricity for a civilian power grid, and the pressurized water design, the PWR, became the dominant reactor type worldwide. Today, roughly 2/3 of all operating nuclear power plants are pressurized water reactors, direct descendants of what Rickover's team built for the Nautilus. The other major type, the boiling water reactor, or BWR, developed by General Electric, takes a slightly different approach. It actually lets the water boil inside the reactor vessel and sends the steam directly to the turbine, eliminating the need for a separate steam generator. It's simpler in some ways, but it means the turbine equipment does come into contact with slightly radioactive steam. So the engineering trade-offs are different. Now, through the late 1950s and into the 1960s, nuclear power entered what you might call its age of optimism. The phrase, "too cheap to meter," gets thrown around a lot. It's attributed to Louis Strauss, chairman of the AEC, in a 1954 speech, though there's some debate about whether he was talking about fission reactors or the dream of fusion power. Either way, the sentiment captured a real mood. Here was an energy source of almost incomprehensible density. One pellet of uranium fuel, about the size of the tip of your little finger, contains as much energy as a ton of coal. A single fuel assembly can power a city block for years. The economics seemed almost too good to be true, and utilities across the United States and Europe began ordering reactors with an enthusiasm that, in retrospect, outpaced the industry's ability to build them well. And this is where the story gets more complicated, because the transition from military precision to commercial scale introduced pressures that Rickover himself had warned about. When you're building reactors for the Navy, cost is a concern, but not the primary driver. Safety and performance come first. Full stop. When you're building reactors for a utility company that needs to deliver returns to shareholders, the calculus shifts. Construction timelines matter. Budget overruns matter. And the regulatory framework for civilian nuclear power was still being invented as the plants were being built. The AEC had a fundamental conflict of interest. It was simultaneously responsible for promoting nuclear energy and for regulating its safety. Imagine the same agency being told to sell you a car and also to decide whether that car is safe to drive. The tension was built into the structure from the beginning, and it would take decades and some very painful lessons to resolve. By the mid-1960s, orders for nuclear plants were accelerating rapidly. General Electric and Westinghouse were competing fiercely for contracts, sometimes offering so-called turnkey deals where they promised to build a complete plant for a fixed price, deals that they actually lost money on, treating them as loss leaders to establish market dominance. Dozens of plants were ordered in what the industry called the Great Bandwagon market of 1966 and 1967. Reactor sizes were scaling up fast, from the modest outputs of early plants to designs promising 1,000 megawatts or more. And with that rapid scaling came questions that hadn't been fully answered yet. Questions about what happens when things go wrong at that scale. Questions about emergency cooling systems, about containment integrity, about the sheer amount of radioactive material sitting inside these increasingly large reactor vessels. The engineering of safety systems in a nuclear plant is fascinating in its own right, because you're designing for events that you hope will never happen, but that you absolutely must be prepared for. The most fundamental concern is something called loss of coolant. What happens if, for whatever reason, the water stops flowing through the reactor core? Remember, even after you shut down the fission chain reaction by inserting the control rods, the fuel is still generating heat. A lot of heat. This is called decay heat, and it comes from the radioactive decay of all those fission products that have accumulated in the fuel. Right after shutdown, decay heat can be 6 or 7% of the reactor's full thermal power. For a large reactor, that's tens of megawatts of heat with nowhere to go if the coolant is lost. And if the fuel gets hot enough, the metal cladding around the fuel pellets, usually an alloy of zirconium, begins to react with steam, generating hydrogen gas and more heat. If temperatures keep climbing, the fuel itself can melt. That's a meltdown, and preventing it is the central preoccupation of nuclear safety engineering. The defense-in-depth philosophy that governs reactor safety is built in layers like the walls of a medieval castle. The first barrier is the ceramic fuel pellet itself, which locks most fission products inside its crystalline structure. The second is the zirconium alloy cladding that surrounds each pellet. The third is the massive steel reactor vessel. The fourth is the containment building, that iconic dome you see at nuclear plants, made of reinforced concrete several feet thick, lined with steel, designed to contain any radioactive release, even if everything inside it goes wrong. And then there are the active safety systems, emergency core cooling systems with multiple redundant trains of pumps and water sources, designed so that even if one system fails, another kicks in. The philosophy is that no single failure, and in many cases, no combination of two failures, should lead to a release of radiation to the environment. But the question that haunted engineers and regulators through the 1970s was whether those systems would actually work when called upon. Because you can't really test an emergency core cooling system at full scale under actual accident conditions. You can't deliberately melt a commercial reactor to see if the safety systems catch it. You rely on analysis, on computer models, on scaled experiments, and on engineering judgment. And in the early 1970s, a series of internal AEC studies raised troubling questions about whether the emergency cooling systems in some plants would perform as designed during a large pipe break. These concerns leaked to the public, fueling a growing anti-nuclear movement that had been gaining strength since the environmental awakening of the late 1960s. And then, on March 28, 1979, at a plant called 3 Mile Island near Harrisburg, Pennsylvania, the theoretical became real. Unit 2 of the 3 Mile Island plant had been operating for just about a year when a feedwater pump tripped in the secondary loop. Now, that might sound minor, a pump stopping in the non-nuclear side of the plant. And honestly, it should have been manageable. Plants are designed to handle that kind of hiccup. But what followed over the next several hours was a cascade of mechanical failures, instrumentation confusion, and human misunderstanding that turned a manageable transient into the worst commercial nuclear accident in American history. Let me walk you through it slowly because the details matter. When the feedwater pump stopped, the steam generators on the secondary side could no longer remove heat from the primary loop effectively. The reactor's control systems did what they were supposed to do. The reactor scrammed, meaning the control rods dropped in and shut down the fission chain reaction within seconds. But here's the thing we talked about earlier. Shutting down the chain reaction doesn't shut down the heat. You still have decay heat from all those accumulated fission products, and in a reactor that's been running at full power, that decay heat is enormous. Something like 6 or 7% of full power right after shutdown, which in a 1,000 megawatt thermal reactor is still tens of megawatts of heat. That heat has to go somewhere. With the feedwater gone, pressure in the primary loop started rising. A relief valve on top of the pressurizer, that's the component that controls pressure in the primary system, opened automatically to vent steam and bring the pressure down. And it worked. Pressure dropped. But here's where the first critical failure happened. The valve was supposed to close again once pressure returned to normal. It didn't. It stuck open. And now you had a pipe, essentially, venting primary coolant, hot radioactive water, out of the reactor system and into a drain tank on the containment floor. Now, the operators in the control room had an indicator light for that valve, but the light only told them whether the electrical signal had been sent to close the valve, not whether the valve had actually closed. The The signal had been sent. The light said closed. But the valve was still open, and coolant was pouring out of the primary system. This is one of those moments where you realize how much depends on the interface between humans and machines. The operators were looking at their instruments, trying to understand what was happening, and the instruments were telling them a story that wasn't quite true. They saw pressure dropping, which made sense if the valve had closed. The system was cooling down after all, since the reactor had scrammed. They saw the pressurizer level, the water level in that pressure-controlling component, actually rising. And this is the detail that really confused them. How could the system be losing coolant but showing a rising water level in the pressurizer? The answer has to do with thermodynamics. As pressure dropped, because coolant was escaping through that stuck valve, some of the superheated water in the primary system began to flash into steam. Steam takes up much more volume than liquid water, and it pushed water up into the pressurizer, making the level indicator go up even though the total amount of coolant in the system was going down. The operators, trained to worry about the pressurizer going solid, completely filled with water, which can cause dangerous pressure spikes, saw that rising level and did exactly the wrong thing. They reduced the flow of emergency cooling water that had automatically kicked in. They were trying to manage what they thought was too much water in the system, when in reality, the system was draining. For over 2 hours, coolant continued to escape through that stuck-open valve. The core began to uncover. Without water surrounding the fuel rods, temperatures climbed rapidly. The zirconium cladding on the fuel rods began reacting with steam at high temperatures, producing hydrogen gas and more heat. Fuel rods warped, cracked, and eventually parts of the core began to melt. About half the core experienced severe damage. Some of the molten material, a mixture of uranium dioxide, zirconium, and steel called corium, slumped to the bottom of the reactor vessel. And yet, and this is important, the reactor vessel held. The containment building held. The massive steel vessel, several inches thick, did not breach. Some radioactive gases were released, primarily xenon and krypton, noble gases that don't accumulate in the body the way iodine or cesium would. The amount of radiation released to the surrounding community was small. The average dose to people living within a few miles of the plant was estimated at about 1 millirem, which is a fraction of what you'd get from a single chest X-ray. No one died from radiation exposure at 3 Mile Island. No one was injured. But the psychological and political impact was enormous. The accident happened just 12 days after the release of a movie called The China Syndrome, a thriller about a nuclear plant cover-up. The timing was almost absurdly dramatic. Public trust in nuclear power, already fraying, collapsed. Over 100,000 people evacuated the area around the plant, many of them terrified by confused and contradictory information from officials who themselves didn't fully understand what was happening inside the reactor. The investigation that followed was exhaustive. The Kemeny Commission, appointed by President Carter, himself a former nuclear submarine officer who'd trained under Rickover, interestingly enough, identified failures at every level. Equipment failures, yes, but more fundamentally, failures of training, of control room design, of communication between operators and regulators, of the entire safety culture surrounding commercial nuclear power. The operators at TMI had not been trained for this specific scenario. Their instruments gave them ambiguous information. Their procedures didn't account for a stuck-open relief valve combined with the confusing pressurizer level readings. The nuclear industry changed profoundly after 3 Mile Island. The Institute of Nuclear Power Operations was created, an industry self-regulatory body focused on operational excellence. Control rooms were redesigned. Training programs were overhauled, with full-scope simulators that could replicate accident scenarios becoming mandatory. The Nuclear Regulatory Commission, which had replaced the AEC's regulatory function in 1975, tightened its oversight. New plants already under construction were completed, mostly, but very few new orders came in. The great expansion of nuclear power in the United States essentially stopped. And then, 7 years later, came Chernobyl, April 26, 1986. And if 3 Mile Island showed what could go wrong in a well-contained Western reactor, Chernobyl showed what happens when fundamental design flaws meet a reckless disregard for safety procedures in a reactor with no containment building to speak of. The Chernobyl plant used RBMK reactors, a Soviet design fundamentally different from the pressurized water reactors we've been talking about. RBMK stands for a Russian phrase meaning high-power channel-type reactor. Instead of using ordinary water as both coolant and moderator, the way a PWR does, the RBMK used graphite as its moderator. Huge blocks of graphite stacked together to form the reactor core, with water flowing through channels in the graphite to cool the fuel and generate steam. And here's the critical difference. In a PWR, if you lose your coolant water, you also lose your moderator, which means the chain reaction slows down. It's an inherent safety feature. But in an RBMK, the graphite moderator stays right there whether the water is present or not. Worse, in certain operating conditions, particularly at low power, the RBMK had what's called a positive void coefficient. That means if the cooling water starts to boil and form steam bubbles, the reactivity actually increases, which makes more heat, which makes more steam, which increases reactivity further. It's a positive feedback loop, the opposite of what you want. On the night of April 25th and into the early hours of the 26th, operators at Chernobyl Unit 4 were conducting a safety test. Ironically, a test of whether the plant's turbines could generate enough electricity during a coast down to power emergency systems in the gap before diesel generators started. The test required running the reactor at low power, and through a series of procedural violations and misunderstandings, the operators brought the reactor down to a much lower power level than intended. At that low power, the reactor became difficult to control. Xenon 135, that same neutron-absorbing fission product that had poisoned Fermi's Hanford reactor back in 1944, was building up in the core, suppressing reactivity. To compensate, the operators withdrew far more control rods than safety rules allowed, leaving the reactor in a deeply unstable configuration. When they initiated the test and the coolant flow changed, that positive void coefficient kicked in. Power surged, not gradually, but explosively. In a matter of seconds, the reactor's thermal output spiked to perhaps 100 times its normal full power. The fuel disintegrated. Steam pressure blew the 1,000-ton reactor lid off the vessel. A second explosion, likely a steam explosion, though some researchers think hydrogen or even a small nuclear excursion contributed, blew open the building. The graphite moderator, now exposed to air, caught fire. Burning graphite sent a plume of radioactive material high into the atmosphere, where winds carried it across Belarus, Ukraine, Scandinavia, and eventually much of Europe. 2 plant workers died that night from the explosions. Over the following days and weeks, 28 more people, mostly firefighters and plant operators who received massive radiation doses, died from acute radiation syndrome. The long-term health effects are harder to quantify and remain debated, but thousands of cases of thyroid cancer, particularly in children who drank milk contaminated with radioactive iodine, have been attributed to the disaster. An exclusion zone of roughly 30 kilometers around the plant was evacuated, and over 100,000 people were permanently relocated. Chernobyl was devastating not just in its immediate human and environmental toll, but in what it did to the global perception of nuclear power. It confirmed the worst fears of the anti-nuclear movement. It made the word nuclear synonymous with catastrophe in many people's minds, and it did this despite the fact that the RBMK design, with its positive void coefficient and lack of containment, was fundamentally different from, and far more dangerous than, the light water reactors used in the West. That distinction was largely lost in the public conversation. But engineers and regulators learned from Chernobyl too. The understanding of how human factors, institutional culture, and reactor physics interact during accidents deepened enormously. The remaining RBMK reactors were modified to reduce their positive void coefficient. International cooperation on nuclear safety expanded, with organizations like the World Association of Nuclear Operators fostering a global safety culture that transcended political boundaries. And for about 2 decades after Chernobyl, nuclear power entered a kind of quiet middle age. Existing plants kept running, and running well, actually. Capacity factors at American nuclear plants climbed from around 50 or 60% in the 1970s to over 90% by the early 2000s, meaning the plants were generating electricity more than 90% of the time. Operational safety records improved dramatically. The plants that were already built became some of the most reliable and productive power sources on the grid. But almost no new ones were ordered in the West. Then, in the early 2000s, something started to shift. Climate change was becoming impossible to ignore, and people began to notice an inconvenient truth about nuclear power. It produces essentially no carbon dioxide during operation. A nuclear plant generates electricity from heat released by splitting atoms, not by burning anything. No coal, no gas, no combustion, no CO2. For people serious about decarbonizing the electricity grid, nuclear started to look less like a relic of the Cold War and more like a necessary tool. There was talk of a nuclear renaissance, new reactor designs, streamlined licensing, a new generation of plants. And some of that momentum was real. New designs were developed, particularly what are called Generation 3 and 3+ reactors, which incorporated lessons from 3 Mile Island and Chernobyl into their fundamental architecture. These designs featured what engineers call passive safety systems, systems that rely on natural forces like gravity, convection, and compressed gas, rather than pumps and diesel generators that need electricity and human action to function. The idea is that even if operators do nothing, even if all power is lost, the reactor will cool itself down safely. The AP1000, designed by Westinghouse, is a good example. In a loss of coolant accident, massive tanks of water above the reactor drain by gravity to flood the core. No pumps needed, no operator action required for at least 72 hours. But then came March 11th, 2011, and a magnitude 9.0 earthquake off the Pacific coast of Japan, and a tsunami that struck the northeast coast of Honshu, with waves that reached heights of over 14 meters in some places. The earthquake itself was one of the most powerful ever recorded. The entire island of Honshu shifted about 2.5 meters to the east, and the Earth's axis wobbled slightly from the redistribution of mass. But it wasn't the shaking that caused the disaster at Fukushima Daiichi. The reactors there, 6 boiling water reactors designed by General Electric, actually did what they were supposed to do when the ground started moving. The control rods inserted automatically. The fission chain reactions stopped within seconds. The earthquake knocked out the external power grid, which was expected. That's what the backup diesel generators were for. And those generators kicked on, right on cue. For about 45 minutes, everything was working. The reactors were shut down, the cooling systems were running on backup power, and the operators were following their procedures. And then the water arrived. The tsunami that hit the Fukushima Daiichi site was roughly 14 to 15 meters high. The plant's seawall was designed for a wave of about 5.5 meters. So the ocean simply came over the wall and flooded the low-lying areas of the plant, where, critically, the diesel generators and their fuel tanks were located. Within minutes, all backup power to units 1 through 4 was lost. And this is where the fundamental physics of nuclear reactors becomes so important, and why we spent all that time earlier talking about how fission works. Because even though the chain reaction had stopped, even though the control rods were fully inserted and no new fission was occurring, the fuel was still incredibly hot. Remember decay heat. When uranium atoms split, some of the fragments they produce are themselves radioactive. They keep decaying, releasing energy for hours and days and weeks after the chain reaction stops. In the first hour after shutdown, a reactor that was producing, say, a gigawatt of thermal power is still generating something like 60 or 70 megawatts of heat from decay alone. That's enough to boil enormous quantities of water. And if you can't remove that heat, if you can't keep water circulating over the fuel, the water that's already there starts to boil away, the fuel rods are exposed, and they begin to overheat. This is exactly what happened at Fukushima. With no electricity to run the pumps, operators had very limited options. They tried using battery-powered systems, steam-driven cooling systems, anything they could manage. Some of these worked for a while, but one by one, the cooling options ran out. In Unit 1, the fuel was likely already partially uncovered within a few hours. As the zirconium cladding on the fuel rods heated past about 1,200 degrees Celsius, it reacted with the surrounding steam to produce hydrogen gas. This is an exothermic reaction. It actually generates more heat, making things worse. And it produces large volumes of hydrogen, which is extremely flammable. That hydrogen accumulated in the upper part of the reactor building, and on March 12th, the day after the earthquake, a hydrogen explosion blew the roof and upper walls off the Unit 1 reactor building. It was a shocking image, broadcast around the world in real time. 2 days later, a similar hydrogen explosion destroyed the upper structure of Unit 3. Unit 2 also experienced severe damage, and Unit 4, which had been shut down for maintenance and had no fuel in its reactor, still suffered a hydrogen explosion, likely from hydrogen that migrated through shared ventilation systems from Unit 3. Here's what's important to understand about Fukushima. The reactor pressure vessels, the thick steel containers holding the fuel, were breached in Units 1, 2, and 3. The fuel melted through the bottom of those vessels in at least Units 1 and 3, and probably Unit 2 as well. This is a full core meltdown, the thing everyone fears most. Molten fuel, called corium, a mixture of uranium dioxide, zirconium, steel, and concrete, collected on the floors of the primary containment structures. Radioactive material was released into the environment, primarily cesium-134 and cesium-137, along with iodine-131 and other fission products. Contaminated water leaked into the ocean. The Japanese government ordered evacuations of progressively larger zones. eventually displacing more than 150,000 people from their homes. And yet, and this is something that often gets lost in the conversation, the direct health impact from radiation exposure at Fukushima has been remarkably limited. As of the most comprehensive studies conducted over the following decade, no deaths have been directly attributed to radiation from the Fukushima accident. The World Health Organization concluded that for the general population, even in the most affected areas, the predicted health risks were low. The real human toll came from the evacuation itself, the stress, the disruption, the elderly patients who died during hurried hospital transfers, the long-term psychological damage of displacement. Some estimates put the number of evacuation-related deaths at over 2,000. That's a genuine tragedy, and it raises difficult questions about how we balance radiation risk against the very real harm of large-scale displacement. Now, I want to sit with that for a moment, because it matters. The engineering failure at Fukushima was real and serious. 3 reactors melted down. Containment was compromised. Radioactive material escaped into the environment. But the containment structures, even damaged, did limit the release enormously compared to Chernobyl, where there was no containment at all, and the health consequences, while still being studied, have been far less severe than the public perception suggests. This isn't to minimize what happened, it's to understand it accurately, because accurate understanding is the only basis for good decisions. The immediate global response was dramatic. Germany, which had been operating 17 nuclear reactors, announced within months that it would phase out nuclear power entirely, and it completed that phase-out in April 2023. Italy reaffirmed its earlier nuclear moratorium in a referendum. Japan itself shut down all of its 54 reactors for safety reviews, and the restart process has been painfully slow. As of recent years, only a fraction have returned to service. In the United States, several reactors that were already struggling economically were shut down ahead of schedule. The nuclear renaissance, which had been tentative to begin with, seemed to evaporate overnight. But here's the thing. The story didn't end there. Because while Fukushima dominated headlines and shaped public opinion, the underlying math of climate change kept getting worse. Carbon emissions continued to rise. The Intergovernmental Panel on Climate Change issued increasingly urgent reports, and the engineering community, along with a growing number of climate scientists and energy analysts, kept pointing to the same uncomfortable fact. Nuclear power is one of the largest sources of carbon-free electricity on the planet. In 2022, nuclear plants generated roughly 10% of the world's electricity, and they did it without burning anything. France, which committed to nuclear power after the oil crisis of 1973, generates about 70% of its electricity from nuclear reactors and has one of the lowest carbon intensities of any industrialized nation's electricity grid. So the conversation started to shift again, slowly. Not a renaissance this time, something more cautious, more pragmatic. People started talking about keeping existing plants open rather than closing them prematurely. In the United States, the Inflation Reduction Act of 2022 included production tax credits for existing nuclear plants, recognizing their value as carbon-free generators. Plants that had been scheduled for early retirement, like the Diablo Canyon plant in California, had their closures reconsidered and ultimately delayed. The logic was straightforward. If you shut down a nuclear plant, you have to replace its output with something, and in practice, that something is often natural gas, which produces CO2. Closing a nuclear plant can actually increase carbon emissions. Germany experienced exactly this. As it phased out nuclear, its coal and gas generation filled part of the gap, complicating its climate goals. And meanwhile, a new generation of reactor designs was taking shape. These aren't your grandmother's nuclear plants. They're smaller, simpler, and designed from the ground up, with the lessons of every previous accident baked into their architecture. Small modular reactors, or SMRs, are one of the most talked about concepts. Instead of building a massive gigawatt-scale plant on-site over a decade, the idea is to build smaller reactors, maybe 50 to 300 megawatts, in a factory, ship them to the site, and assemble them. Factory construction means better quality control, lower costs through standardization, and faster deployment. NuScale Power in the United States received design certification from the Nuclear Regulatory Commission for its SMR in 2023, though its first planned project in Idaho was subsequently canceled due to rising cost estimates. A reminder that the economics of nuclear power remain genuinely challenging. Other designs go even further from the conventional light water reactor model. Molten salt reactors, for instance, dissolve the nuclear fuel directly in a liquid salt mixture. There's no solid fuel to melt down because the fuel is already liquid. If the reactor overheats, a freeze plug at the bottom melts and the fuel drains by gravity into a tank where it spreads out and cools. It's an inherently self-limiting design. High-temperature gas-cooled reactors use helium as a coolant and graphite-coated fuel particles that can withstand extreme temperatures without releasing fission products. Some designs aim to use thorium instead of uranium. Thorium is about 3 times more abundant in the Earth's crust and produces less long-lived radioactive waste. None of these are science fiction. Several are in advanced development or prototype stages in the United States, Canada, China, and elsewhere. And then there's fusion. We've been talking this whole time about fission, splitting heavy atoms apart. Fusion is the opposite, taking light atoms, usually isotopes of hydrogen, called deuterium and tritium, and forcing them together to form helium. This is what powers the sun. The energy released per reaction is enormous, and the fuel is virtually unlimited. Deuterium can be extracted from seawater. Fusion produces no long-lived radioactive waste and carries no risk of a meltdown because the reaction is so difficult to sustain that any disruption simply stops it. The challenge is achieving the conditions necessary for fusion. Temperatures of over 100 million degrees Celsius, at which the fuel becomes a plasma, and keeping that plasma confined long enough for enough reactions to occur. For decades, fusion has been 30 years away, and that's been a running joke in the energy world. But recent progress has been genuinely remarkable. In December 2022, the National Ignition Facility at Lawrence Livermore National Laboratory achieved fusion ignition for the first time. The fusion reactions produced more energy than the laser energy used to trigger them. It was a proof of concept, not a power plant, but it was a milestone that had been pursued for over 60 years. Meanwhile, the ITER project in southern France, a massive international collaboration, is building the world's largest tokamak, a donut-shaped magnetic confinement device aimed at demonstrating sustained fusion power production in the 2030s. And dozens of private companies, funded by billions in venture capital, are pursuing alternative fusion approaches with aggressive timelines. So where does all of this leave us? You're lying here, maybe drifting in and out, and we've traveled an enormous distance together. From Democritus imagining invisible atoms in ancient Greece, to Becquerel's photographic plates fogging in a drawer in Paris, to Rutherford's gold foil experiment revealing the tiny dense nucleus, to Hahn and Strassmann splitting uranium in Berlin on the eve of war. From the secret cities of the Manhattan Project to the blinding flash over the New Mexico desert, from Rickover's stubborn insistence on a pressurized water reactor for his submarine to the first commercial nuclear plant at Shippingport, from the stuck valve at 3 Mile Island to the reckless experiment at Chernobyl to the towering wave at Fukushima, each of these moments changed the trajectory of this technology, and each one taught us something, sometimes at terrible cost. The story of nuclear power is really a story about humanity's relationship with the forces of nature. We figured out that the nucleus of an atom contains an almost unimaginable amount of energy. We learned how to release it. We used it first for destruction, then tried to harness it for creation. We built machines of extraordinary complexity to control a process that, at its heart, is about managing the same fire that lights the stars. And we've made mistakes, serious ones, and we've learned from them, and we've argued endlessly about whether the risks are worth the rewards. What's remarkable, when you step back, is how much of the story comes down to engineering, to the careful, painstaking work of designing systems that contain enormous energies safely, day after day, year after year. The fuel pellets stacked in their zirconium cladding, the pressure vessel forged from a single ingot of steel, the containment building with its thick concrete walls, the redundant cooling systems, the backup generators, the control rods poised above the core, ready to drop. Layer after layer of protection, each one designed by someone who thought carefully about what could go wrong. That's what engineering is, really. It's applied worry. It's the discipline of imagining failure so thoroughly that you can design against it. And tonight, wherever you are, the quiet hum of civilization around you is powered in part by this technology. Somewhere, not so far away, water is circulating through a reactor core, carrying heat to a steam generator, spinning a turbine, pushing electrons through copper wire and out into the grid that keeps your lights on, your phone charged, your world running. It's happening right now, as you lie here, and it will keep happening through the night, steady and patient and unseen. The atoms are splitting, one by one, releasing their ancient energy, and someone is watching the instruments, making sure everything is exactly as it should be. That's a comforting thought, in its own way. All that invisible energy, all that careful engineering, all those lessons learned, working quietly in the dark while you rest. So let that thought settle. Let it be the last thing on your mind as you drift off. The quiet, steady hum of atoms doing their work, and the long, extraordinary story of how we learned to listen to them.